Hello everyone, I am Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course Operating Systems. In this lecture, let us see about the other preemptive scheduling algorithm, shortest remaining time first. Up to our last lecture, we have learned different types of CPU scheduling algorithms. We have already learned three types of preemptive, non-preemptive scheduling algorithm, that is FCFS, SJF, and priority. In the last lecture, we have learned about preemptive CPU scheduling algorithm, which is round robin. I hope you all are clear with those lectures. In this lecture, let us understand what actually the shortest remaining time first algorithm is. So before proceeding with the example, make a note of some examples here. So like some key points. This shortest remaining time first algorithm is also called as shortest job first of preemptive nature. Remember, we have already learned about shortest job first, which is non-preemptive, where we have understood like if you have some set of processes that are available in the ready queue, the process that requires less CPU time will be given a chance to be executed by the CPU. That is what we have learned. Now, in this approach of which is called as shortest remaining time first, and this what happens whenever a new process arrives. So you can understand here, we are executing some process. Already CPU is executing one process. Now, if a new process arrives, then we need to check its burst time. Now, if the new process burst time is less than the remaining burst time of the present running CPU running process, then it has to be preempted. That means the currently running process has to be forcibly stopped and the CPU will be given a chance to be executed by the new process. I'll repeat once again. Let us consider we are executing a process P1. Okay. And while executing, let us consider a new process has come into our ready queue. That is called as P2. Let us consider P2 requires 2 seconds of time. Why? At this particular time, we are in the Gantt chart. Let us consider at this particular time, P2 has arrived. Now, at this particular time, P3 requires 3 more seconds to be executed, but P2 requires 2 seconds only. This is the new process that has arrived in the ready queue. Now, what the CPU will do? This process will be preempted and it will be added to the ready queue and process P2 will be brought and it will be executed by the CPU. That is what I am telling here. Whenever a new process arrives, then the CPU will check the remaining time of the present running process and the burst time required of the current process, and whichever is less, that will be executed. Suppose if this process requires less time, then this will be continued. But in our example, if you see, because P2 requires 2 seconds and P3 requires 3 seconds, this will be preempted. That means forcibly it will be removed from this Gantt chart and it will be added to the ready queue, and then CPU will start executing this P2. Okay, so make this little even more clear. Let us run how this shortest remaining time first. Remember, shortest job first preemptive is also called as shortest remaining time first. Okay, why it is called as shortest remaining time first? Because whichever time is having less remaining time, that will be executed. That's why it is named as shortest remaining time. This is a preemptive algorithm. This is also called as shortest job first preemptive algorithm. Right? So let us understand with one example. I have considered a small example here where only 3 processes are there, P1, P2 and P3, and each process what is the required burst time and what is the arrival time also mentioned in the table. Now let us understand how SRTF is nothing but shortest remaining time first will be executed. Right now, always remember we need to maintain a timer, and that timer each second it will increase, and each second we need to check any process is arriving or not. Okay. Now at time interval 0 seconds, we got, let us consider this is our ready queue. Okay, and in the ready queue we got process P1, and now this is the only process available, so we will be selecting this one, and that has been added to the Gantt chart. Now, this requires, you can see in the diagram, 4 seconds. Let us execute this one for 1 second. Okay. Observe here in the ready queue, nothing is there as of now because P1 is there earlier and P1 has been removed to execute. Okay, now we will execute for 1 second. At 1 second, you got to see we got a new process, that is P2. Now, as per this SRTF, that is shortest remaining time first, whenever new process arrives, that is P2 in our case, we need to check what is the time required for P2, it is 2 seconds, and what is the remaining time of P1. Already we have executed 1 second, and so out of 4 seconds, 1 second executed means it requires 3 more seconds. In between these two, if you can see which process requires less time, T2 requires less time, that is 2 seconds. So in that case, what happens? P1 will be preempted. That means P1 will be added to the ready queue and P2 will be given a chance to be executed. Got it, all of you? Right, that is why it is called as shortest the remaining time first, whichever will have the less time. Even if the presently running process, if it requires less time compared to the new process, that will be continued, no issue in that. Okay, now up to now I think you all are clear. Now let us understand. P2 requires 2 seconds, let us execute one more second. At 2 seconds, if you see, we got now in the ready queue, you can see only P process is there. Earlier P1 and then P2. For your understanding, I'm writing, and P1 is now only P1 is there. Now P5 has been added. Now whenever a new process comes, what we need to check? We need to check the remaining time. What is the remaining time of P2? That is 1 second. And what is the time required for P3? Sorry, not it is P5, it is P3. What is the time required for P3? 5 seconds. Isn't it or not? Now between these two, this is less. So we need to continue with P2. So P2 will execute one more second. So it will finish. It will finish because it requires 2 seconds only. So P2 has completed its execution. Now in the ready queue, do you remember? We got P1 deleted, P2 deleted, we got P1 and P5. This is how, sorry, P3. This is how the thing is. So now P1, P3, we have two processes. Now which process has to be taken? The process which requires less CPU time. Now, which process? You can see P1 requires 3 seconds, P3 requires 5 seconds. So the chance will be given to P1, which will be executed for 4th second. You can always need to keep a track of new process any arriving at that particular second. In our example, after 2 seconds, nothing is there. So I'm just ignoring that. So P remaining 2 seconds it will execute. So 3 to 4 to 5 to 6 seconds it has executed. Like up to 6 seconds it has executed. Total of 4 seconds it has done its execution. Now the only process that is available with us is P3. Observe here, I am doing one more alteration here. Whichever process has completed its execution, I have turned them into red color. Okay, now only process that is available in our ready queue is that is P5 and sorry P3, that will be given a chance. Now no process is there, so continue execution up to 11 seconds because it requires 5 seconds. So you can see P5 plus that means 6 plus 5, which is 11 seconds, right? So this is how shortest job first preemptive scheduling algorithm will work. Now let us calculate how the waiting time will be calculated. You all know the formula for waiting time. Start time minus arrival time plus any time it is waiting for the next process. Why? Because there are chances in the preemptive at one stretch it will not execute, it will not complete its execution. There will be some slots given depending upon the algorithm. So we need to consider the waiting time also in case of calculating the overall waiting time for a particular process. You see for P1, the start time is 0. The arrival time is 0 and also from here to here it is waiting, isn't it or not? So what is that? It is waiting 3 minus 2, it is 1. So it is waiting for 2 more seconds, that also to be added. So the total waiting time for P1 is 2. For P2 you can see 1 minus 1 and no way P2 is waiting, isn't it or not? So no need to consider that, we can continue with that, right? No. So for P3 it is also like that, 6 minus 2 and nowhere it is waiting. So that is how it will be executed, right? Alright. Now turnaround time is nothing but completion time minus arrival time. Completion time is nothing but at what time it will complete. You can see for P1, you can see it is completing at this second. See here. Okay, so 6 minus 0, which is 6. P2 is completing at 3 seconds. So 3 minus 1 is 2. And P3 is completing at 11 seconds. 11 minus 2 is 9. Right? So this is how the simple, this is a simple example where 3 processes are considered. I hope you all are clear with this example. For even more clarity, I have considered one more example where 5 processes are considered and the burst time and arrival time are done. Let us see how this is executed. Okay. At timer 0, same approach, no need to confuse. Just I'm maintaining one ready queue here. At process, this is the ready queue. Okay. At time 0, process P4 has arrived. So P4 will start its execution. And then at 1 seconds, you can see P3 has arrived. P3 will be added to the ready queue. And to always remember, you need to check the remaining time of current process and the new process required time. Okay, in our case, P4 requires 2 more seconds to execute. Out of 3, it has executed 1 second. It requires 2 more seconds, right? Sorry, 2 seconds has been executed. So it requires 1 more seconds to execute. And 1 is less than 8. So it will continue executing with P4 only. So P4, you can see at 2 seconds, we got one more process, which is P1. P1 will be added to the ready queue and P4 will continue its execution and P4 has completed its execution. That's why it has been turned to red. You can see here, right? Now we got 2 processes in the ready queue. What are they? P3 and P1. Now out of these 2 processes, which process is having the smallest burst time, that will be considered. Now you can see in the diagram, P3 requires 8 seconds and P1 requires 6 seconds. So P1 will be given a chance to be executed. Understand here, if this is first come first serve approach, P3 should be given a chance. But because it is shortest remaining time first, the process which requires less time, that has to be given a chance. In our case, 6. So 6 will be given. That means P1 will be given a chance to be executed. At each second, we need to check the arrival time also. Okay. So now P1 has executed for 1 second. That is, we are in the 4th second. You can see at 4th second, we got P5. So P5 will be added to the ready queue. And we need to check what is the time required for P5, 4 seconds, and this requires 5 seconds. Now, which one should be given a chance? I'll pause for 2 seconds. Which one will be given a chance? Yes, P5 will be given a chance because it requires less time. Okay, right? So P5 will be given a chance and it will be executed for 1 second. And you can see at the 5th second, P2 has arrived. Its required time is 2 seconds. P5, what is the current process? 3 seconds. Then what happens? P5 has to be resumed and then it has to be added to the ready queue and P2 will be given a chance to be executed. I hope you all are understanding. Now, in the similar fashion, if you proceed, similar fashion, I'm not going to again the same thing. Similar fashion, if you execute, you can see at 23 seconds, we got to execute all the process. So all the processes have completed its execution. Only thing you need to remember here is whenever you are executing one process and at a particular time a new process arrives, its CPU time and the currently running process remaining CPU time we need to compare. Whichever is less, that has to be executed next. Right? So with this information, let us calculate the waiting time. For P4, you already know the waiting time formula is start time minus arrival time plus waiting time. If anything happens here, for P4, you can see it's 0 minus 0 and nowhere P4 is waiting in our ready queue. So it is 0. Right? For P1, you can see it is 3 minus 2 plus anywhere P1 is waiting. Yes, from here to here it is waiting. Isn't it or no? So you can see from there to there it is waiting. So its time is 5. 5 minus 4 is 1 and here it is 2, 3 and here it is 3. So total of 6 seconds. So total of 7 seconds is the waiting time. Similar fashion, if you proceed, P2 0, P5 2 and P3 14. So the average waiting time is total of all these values by total number of processes, which is 5 in our case. So this is the average waiting time. I just want to tell you, I have considered the same example for all the other algorithms also. If you want, you can compare the average waiting time, how much you have got for the other algorithms like FCFS, SJF, priority and all. Observe how, what is the average waiting time we are getting for the same example. I have been using the same example for all the algorithms. All right. Now, for the same example, what is the turnaround time? You already know turnaround time is nothing but completion time minus arrival time. Same example, like same the formula I have used. So P4, you can see 3 minus 0, which is 3. For P1, when it has completed 15 seconds minus 2, which is 13. And for P2, you can see P2 has completed 7 seconds minus 5, which is 2. And for P5, you can see 10 minus 4, which is 6. And for P3, you can see 23 minus 1, which is 20. Right? So the average turnaround time will be total of these values by 5. Right? So this is about the shortest remaining time first. Now, the problem with this algorithm, like we cannot say problem, you need to have an observation here, like it suffers from starvation. What do you mean by starvation is, suppose if a process is executing, CPU is executing this process. Now, a new process comes, which is P2. Now, if this process CPU time is less, then CPU will be cancelling this one and it will go to P2. Now, after executing this one, again the chance will be given to P1. Again, while executing P1, let us consider another new process comes, which is P3. Okay. Now, P3 also having less time when compared to the remaining time of this one, then CPU will cancel this one and the CPU will be given to P3. That means P1 will never get a chance if its remaining time is larger than the new process that is arriving. That means it keeps on waiting for its turn to be executed by the CPU. That is called as starvation. It keeps on waiting for its turn to execute because of its largest CPU time requirement. Right. So this is called as starvation, and that is the only observation that we got from this shortest remaining time first. Right. Now here I have given you one assignment. Just make a note of these 5 processes with the burst time and arrival time. Try to calculate the average waiting time and average turnaround time using this shortest remaining time first algorithm. Right? I hope you all are clear with this today's lecture. Let us all meet in the next lecture. And thank you all of you.